Hello and welcome to this video on finding a basis for the column space of a matrix. So in this video I'm going to start off by going over a couple definitions of things you've probably already seen. I'm sure I know in past videos I put up, if you've been following, you've seen these definitions, but just to recap what the column space of a matrix is, and also what does it mean for a set of vectors to be a basis of a vector space. And then I'll go into several examples for the rest of the video, where I'm given a matrix and asked to find, the column space for that matrix and also a basis for that column space. All right. So what is the column space of a matrix? So suppose we're given an m by n matrix, right? M rows, n columns, and I've written it like this, where you have the matrix brackets here, and there are n columns, see A1, A2, all the way up to AN, and each of these n columns is going to have m components in it, right? So each of these column vectors are from Rm, right? Euclidean space Rm, right? Vectors with m components, that'll make up the m rows going across. So the column space of matrix A is the subspace of Rm, right? So it's also a vector space, right? It satisfies all 10 vector space axioms, but is a subset of Rm. So it's a subspace of Rm spanned by the column vectors of A, right? And those would be that A1, A2, AN that I wrote up here. Now the way this is denoted is, cola, the column space of A, right? COL, and then in parentheses the matrix, the name of the matrix. So the column space of A is, the span of the column vectors of A, or the columns of A. Now don't forget what, again, this is something I'm assuming you've seen. The span of a set of vectors is just the set of all linear combinations of those vectors. So you could also say that the column space of A is the set of linear combinations of the vectors A1 through AN, right? The columns of A, where I have, x1 times A1, where these x's are scalars, and I accidentally put a little smudge up here, so there should be nothing here. That's why I wrote scalar above here, sorry. x1a1 plus x2a2 plus, all the way up to xn an. The a's are the column vectors from, the columns of matrix A, and all these x's are scalars, right? Here my scalars are going to be from the set of real numbers. Okay, so again, hopefully you're familiar with span by now, right? So the column space is simply a span of the columns of A, right? And then something else I'm assuming you're somewhat familiar with before watching this, the basis of a vector space, or a basis, not the basis, right? Bases of vector spaces are not unique. More than one for, a vector space. So given a vector space V, a set of vectors from V, right, say S, which has vectors, V1, V2, all the way up to say Vn, right, all these vectors are from some vector space V, is a basis for V if, one, S spans V, right, and this is, just saying that, V equals the span of S, same thing. Right, that just means every vector in the vector space can be written as a linear combination of the vectors in S, right? These vectors here. And 2, S is a set of, linearly independent vectors. And what that means is that none of the vectors in S, right, none of these, can be written as a linear combination of the other vectors in S. Right. And a more proper way of saying this is that if you were to take, say, x1 v1 plus x2 v2, where the v guys are my vectors, and these x's are scalars, like on the previous page, plus all the way up to xn vn. It's a v. And you were to set that equal to the 0 vector, right? You're asking what linear combinations of these vectors make the 0 vector? Well, the obvious one is when all the scalars are 0, right? That's just the trivial solution, right? The simple one, the obvious one, right? The trivial solution is when every single one of the scalars is simply the number 0, right? If I take 0 of all the vectors, I'm going to get 0 vector back. If the trivial solution is the only solution, then you have a set of linearly independent vectors. And again, hopefully this is all familiar to you at this point. Alright, so for the rest of the video, I just have some examples of matrices of different sizes. Some of them are the same size, but it ranges from I got 2x3, I got some 3x4s, 3x3. And I'm asked to find the column space, describe the column space of that matrix, and then we'll go about finding a basis for that the column space of the matrix. Alright, so my first example, I have a 2x3 matrix here. So I'm asked to find the column space of matrix A, denoted with that col-a, right? Column of A, column space of A. Then find a basis for the column space of A. Alright, so the column vectors here are this negative 1, 1, -1, right? I'll call that, like I was doing on the first page, I'll call that vector A1. And then there's another column vector 5 with components 5, -6. I'll call that A2. And column vector with the two components 8, 1. I'll call that A3. And you notice how these all belong to R2, right? Each of them has two components, right? So all three of these belong to R2. And so the column space is easy to describe, right? If you're looking at a matrix, you see the columns. The column space, right, is very simple to describe in the beginning, and then we're going to actually, once we find a basis for the column space, I'm going to then rewrite a description of the column space in even simpler terms. Right, but for right now, the column space of A is the span of the set with these three vectors in it, right? With the vector from R2, this 1, -1, the column vector 5, -6, and the column vector 8, 1. Alright, or another way to write it, as I was saying on the last the page right before this, it's just the set of all linear what is the span of a set of vectors, but the set of linear combinations of those vectors. So it's every single vector that looks like this: x1 times 1, -1, plus x2 times the 5, -6, plus an x3 times the vector 8, 1, such that x1, x2, and x3 are real, right? They are scalars, belong to the real numbers. Right, sorry about the cutoff on the end of the page there, the wraparound here. Hopefully this makes sense. Right. So like I said, there's part 1. Right. That's a nice description of the column space. I've done the first part. When we're done finding a basis, I will go back and actually simplify this. Okay. Alright, so when I'm going now into finding a basis, or remember a basis, you could think of a basis as the building blocks for a vector space, right? Because this is a vector space here, right? In fact, the column space of A in this example is a subspace of R2, right? All the vectors are going to belong to R2. So every vector in this is an R2, and it also forms a vector space, right? Therefore, a subspace of R2. Now, when you talk about finding a basis for a vector space, really you're kind of talking about finding the some building blocks. Can I find a set of vectors such that I can use those vectors to create every vector in the space? And are they independent, right? Do I need all of them, right? Or are they dependent? Are there some of them I don't need? And then you get rid of the ones you don't need. You're trying to get down to a simple structure, a simple set of building blocks when you're creating a basis for a vector space. Right. So when I go now to finding a basis for the column space of A, most obvious candidate here would be, well, what about this set of vectors? All right, so that'll be the first question I ask in these problems. Are the columns themselves, right, the set with those columns, a basis for the column space? So how about, is this set with 1, -1, 5, -6, and 8, 1 here, is this a basis for the column space of A? And you know what, I'm going to call this just S like I did in the last page, some set of S for set, all right, set of vectors. Now it's obvious, hopefully, by the definition of span, we do have S spans the column space of A. That's good. All right, that was number 1. I need that to happen, right? And it's by definition of span, right? What is the column space of A? It's all linear combinations of these 3 vectors, right? So every vector in the column space can be written as a linear combination of these 3 vectors. So by definition, S spans the column space of A. But S is linearly dependent, right? It's not a set of independent vectors, and we'll see why here in a second. S is linearly dependent. Uh-oh. Right. Now, why is that? All right, that's bad. Now, if you've seen other videos of mine on finding a basis for a span of vectors, or just finding a basis of a set of a vector space in general, when the number of vectors in a set is greater than the number of components that those vectors have, right? So there are 3 vectors and only 2 components in the vectors. Then you'll have a linearly dependent set. And again, I showed that, talked about that in a previous video. So this is a linearly dependent set, meaning that S here, this set of the 3 vectors that I started with, the 3 columns of A, is not a basis for the column space of A. All right. So what is? Well, what we're going to do is, instead of S being a basis, because it's not, we're going to find a subset of S, right? Maybe one of these vectors, maybe just 2 of them, will be a basis for the column space. Well, that's going to go back into, let me show you. I said S is linearly dependent because of a shortcut, but normally I would do this, right? To show this, we're going to, you look at the equation look at the equation, where I have when is a linear combination of these three, right? So sum x1 times 1 negative 1, sorry, plus sum x2 times 5 negative 6 plus sum x3 times 8 1. When you're testing for independence, you're asking what linear combinations of the vectors in the set, right? That's what I've got here, is going to be equal to the 0 vector. Now the 0 vector in R2 is that vector with two zeros, right? 0, 0. Alright, now this corresponds to a system of equations. Now I'm just going to jump right now to the augmented matrix for that system involving x1, x2, x3. So, it leads me to a system of equations where, if you look at the first components, you'd have x1 plus, 5x2 plus 8x3 would be equal to 0. You know what? Instead of skipping to the augmented matrix, I'll actually write the system this time. I'll do the shortcuts in the next examples. So for the first components of these vectors, we'd have x1, plus 5x2 plus 8x3 is equal to 0. And then for the second components, in order for this sum to be equal to 0, I have negative x1 minus 6x2 and then plus x3, right, is equal to 0. All right. Now I'll go to the augmented matrix for that system. Now you can write this as a matrix equation where you have the product of two matrices, right? The coefficient matrix times the variable matrix equals the 0 matrix. But I'll write just the augmented matrix for this system. So down the first column, right, you have the coefficients of x1, which are just this first vector, the first column of matrix A. So 1, negative 1. And then down the second column, the coefficients of x2, or just the second vector, the second column from matrix A, and then so 5, negative 6. And then the coefficients of x3, 8, 1, and equals, and then you got zeros on the other side. All right. But do you notice how this matrix, what's over here to the left of the bar, right, is just matrix A again, right, that 2 by 3 matrix I started with, the 1, negative 1, 5, negative 6, 8, 1 that I started with, is what's to the left of the bar here. Alright, and then we were trying to solve a system, and once I had the augmented matrix for a system, I would like to use row operations and put that into reduced echelon form or reduced row echelon form. Now if you're doing that, you can do it by hand, which there's only 2 rows here. I'm going to do that here, or we can go to a calculator, but I'll do calculator stuff later. Now I'm just going to kind of scratch some stuff off here, so bear with me. So I would, if I have look at the first row, got my leading 1, my first pivot position right here. Want zeros below and above it. Well, there's nothing above it, so there's zeros below it. I would just add the first row, the second row. Right, that would give me a 0 here. Now this isn't matrix A anymore. Okay. That would give me a 0 here, and then add this to this. That would give me negative 1 here. Add this to this. That would give me 9 here. Okay, and then this will always be 0. So really I'm only playing around with the matrix where matrix A was, right, to the left of the bar. Then I would multiply this row by 5, because now, this is my pivot position now. I'm done with this, this pivot position. I got zeros below it and above it. Next row, the first non-zero entry is this negative 1. Got, I want zeros above it. I'd multiply this by 5 to make it negative 5 and then add it to this. Alright, so that make this into 0 now. And then 5 times this would be 45. And then 45 plus 8 would be 53. Right. And then and that's it, right? Then the zeros over here are always zeros. And then finally I would multiply this, because I want to lead in row reduced echelon form, the pivot position, the first non-zero entry in a row going from left to right has to be +1. I would just multiply this by -1 and this by -1, so you'd have 1 here and -9 there. Right. So when all's said and done here, this matrix in reduced echelon form looks like this: 1, 0, and then 0, 1, and 53, -9. And then I've got, again, the 0. Sometimes we're not even going to concern ourselves with the zeros over here. Instead, we'll just look at the matrix A. All I did was take the matrix A, really, and put it into reduced row echelon form. Now, if you look at this, right, look at the pivot positions. Right, look at where the pivot positions are. Those leading non-zero, those leading ones in the rows. You see that very clearly. The first pivot position here is in the first column, and that first column corresponded to coefficients of this x1, right? So x1 is what they call a basic variable, any variables corresponding to pivot columns. The second row, the pivot position, that first one there is in the second column, and that corresponded to this column of coefficients of x2. So x2 is also considered a basic variable. And then the third column, right, doesn't have any of these leading ones, and it doesn't have a pivot position in it. So, and those corresponded to coefficients of x3. All right, so x3 is what they would call a free variable. All right, so that means I could replace x3 with any real number I wished. Right, and then once I did that, the value of x1 and x2 would then be fixed. Right? I'd have to be I couldn't just let x1 and x2 be anything I wanted, just x3. And what I like to do, and you've seen me do this in past videos, again if you've been watching, you could leave the free variables the way they are, leave this as x3, that's fine, but I personally like replacing my free variables with other parameters, other variables, other variable expressions that represent a real number, right? And as long as it's an expression that can take on any real number value, you're fine. So I let x3 be equal to, say, t, where the value of t is any real number. Any real number I want it to be. Right? So obviously this is going to that's why this set is dependent, right? That's why S is linearly dependent, because this equation here doesn't have just the trivial solution, right, where x1, x2, and x3 are all 0. That's the obvious one, but it's going to have other solutions other than that. It's going to have non-trivial solutions for just different choices of my variable t down here. All right, let's actually describe those. All right, so if you look at the first row of the reduced echelon form matrix, this implies that I have x1, right, 1x1 plus no x2 plus 53 x3, or 53 times t, would be equal to 0, implying that the value of x1 would be negative 53 times whatever I choose for t. All right. Okay, and then this row isn't telling me that the value of x2 minus 9t, right, minus 9 times this x3, but I'm calling it t, is equal to 0. And therefore x2 must be equal to positive 9t. All right, so the solutions of this equation up here. Right. So the solutions of this equation, I can replace x1 with negative 53 times whatever I want for t. The value of x2 is going to be 9 times, again, whatever I choose for t, and the value of x3 is going to be this this choice of t, right? So again, definitely S is dependent, right? The set of vectors is dependent for sure. All right, and you could go ahead and play around with it, right? That means I could replace, test it out. I could replace, obviously if I replace t equals 0, you get that trivial solution, but that's not interesting. All right, there's more to it than that. All right, if t were equal to 1, you'd have x1 is negative 53, x2 is 9, and x3 is 1. And then you could check it out, say take negative 53 times that first vector times 1, negative 1, right? I'm just replacing x1, x2, and x3 with these numbers here. That plus 9 times the second vector, 5, negative 6, and then plus 1 of the third vector, right, plus 8, 1, should be equal to the 0 vector. Right. And then, you can double check this. Negative 53 plus 45 is negative 8 plus 8 is 0. Then 53 minus 45. Oh, that's not 45. 53 minus 54 is negative 1 plus 1 is 0. And then you get 0, 0. This works. And then you can see why the vectors are dependent now. When you look at this, this is, again, a non-trivial, any non-trivial solution can show you how the vectors are actually dependent. Right? Because you could take this equation I've written down here and solve for one of these, right? So, like, say I solve for the vector 8, 1 here. Like say I wanted to get that alone. Let me bubble it. All I would do is add 53, add this and subtract this, and we'd see that 8, 1 would be equal to 53 times 1, negative 1, and then minus 9 times 5, negative 6. Right, we'd see that. And so definitely S is dependent, right? That you can write one of the vectors as a linear combination of the others. Right. Okay, so sorry, that was pretty long-winded there, but since S is not a basis, how do I find a basis? Right. Well, I kind of gave you a hint down here. Because this vector 8, 1 can be written as a linear combination of these two, I don't need 8, 1 in my set. Right, when I'm trying to construct the building blocks, it's not necessary, because I can build 8, 1 out of 1, negative 1, and 5, negative 6 in this way. Take 53 of this and minus 9 of that. Right. And the key is, right, so you might be asking, what vectors do I remove? Right, if a set is dependent, like this is, right, this set with the 3 vectors, if this set is dependent, what vectors do I need to remove to make it independent? Well, where that comes in, that's where the reduced echelon form, or just or just regular echelon form you could look at as well, because they'll have the same pivot columns. But let me show you. So how do I determine which vectors in the set are independent? So I'll rewrite this, and I'll ask that question on the following page. Right, so next page. So how do I determine, so if S is dependent, right? So if S is dependent, how do you determine which vectors in S would be independent? And this involves putting that matrix A in reduced echelon form. So remember, I started off with, now this time I'm not going to write the, I'll write the zeros on the other side, why not? So this time I write, 1, -1, 5, -6, the 8, 1, and then, that same matrix we had earlier. And when I put this into the reduced echelon form, 0, 0, 1, 53, -9, and then again this is just zeros over here, right? So what you're going to see is that your pivot columns will correspond to the vectors of the original set that would be independent, that would form an independent set. So 1, -1, and 5, -6, and I'll write that note down here. Right, the pivot columns in reduced echelon form, or again, even just regular row echelon form or echelon form. But I like reduced, right? I like having zeros above and below. It just makes things easier for me. Pivot columns in reduced echelon form will correspond to vectors in the set to vectors that form an independent set. I'll say to vectors that form an independent set. Alright, so now again, not these columns themselves. Alright, not ones. I mean, 1, 0 and 0, 1. I mean, they are independent as well. But again, I'm just gonna be looking for vectors in the set itself that form an independent set at this moment. And then these free variable columns. So this column here corresponds to the column that's not a pivot column, that doesn't have a pivot position in it. Corresponds to the set of the vectors you don't need, right? Like I can get rid of that, So the non-pivot columns correspond to the vectors in the set that are unnecessary. So again, I can like scratch out the vector 8, 1. And you saw again earlier, you saw 8, 1 can be written as a linear combination of this 1, -1, and 5, -6. So again, it's really not needed. And that tells me too that every vector in this set, this column space, going way back here now. So you know how the column space of A I said was the span of these three. Well, you don't need one of them, all right? 8, 1 is unnecessary. Scratch it off. And now I'm saying the column space of A is the span of just these two, all right? Which again corresponded to the pivot columns in reduced echelon form. All right, and then this set of these two vectors do form a basis for the column space of A. Right? So at the very end here, the column space of A is now, I can just write it as, now it's just the span of these two vectors, 1, -1, and 5, -6. Because again, this set of vectors, and this set of vectors spans the space, of course, by definition. Every vector in the column space of A can be written as a linear combination of these two. and these two are independent, as we've seen, right, with the little reduced echelon form session there. Right. Or you could just say, hey, there's only two vectors and they're not scalar multiples of each other, so they're independent. And again, so this set with the this set with the vectors 1, -1 and 5, -6, that set forms a basis for the column space of A. All right, that's a simple set of building blocks for the column space. Every vector in the column space can be built by using these two vectors, and these two vectors are both necessary, right? Because they can't be written as linear combinations of each other or scalar multiples of each other. I need them both to be able to construct a column space. Right. Additionally here, since the column space has a these are vectors from R2, and I have a basis with two vectors. I don't know if you recall, hopefully you do, that remember the dimension of R2 was 2. It's two-dimensional. Every basis of R2 is going to have two vectors in it. So that tells me also that the column space of A is all of R2. We could also say that. Every vector in R2 can be written as a linear combination of these two, and these two vectors are independent. I agree. But the key is, right, the shortcut, and what I'm going to be doing from here on out is just writing my matrix, again, ignoring the zeros. I'm going to stop writing these zeros. And just writing the matrix that we're given in reduced echelon form, looking for pivot columns, and what vectors, what columns in the matrix correspond to those pivot columns. It's really that simple in the end. Okay, so that one I did the long way. So now the rest of the time I'm going to be kind of just doing some shortcuts here for you. All right. Okay. So here, same question. All right. Here's matrix A. It's another 2 by 3. All right. So now you might be thinking, hey, the last matrix was a 2 by 3, and I just eliminated the third column, and that was the only one I needed to get rid of. That's not always going to happen. Okay. Just be careful with that. Just because you see one example work out one way doesn't mean all examples that look like that are going to be the same, right? Which you'll see here. Okay. All right. So the column space of A is again the span of the three column vectors, right? So the span of 1, -2, the vector 4, -8, and -3, 6. All right, and as before, these are all vectors from R2, all right, two components again. And the column space of A, I'll write it's a vector space, right? The span of a set of vectors will be a vector space, and it's a subset of R2, so it's a subspace of R2. Alright, so now how do we determine a basis? Alright, I've described the column space. I might reduce that a little bit, because you already can hopefully tell that this set of vectors, right, is going to be dependent, right? Because there are more vectors than there are components of the vectors. So what I'm going to do now is take my matrix here. If I was to try to test for independence, or even test to see if it spans, it's by definition this set spans the column space. So it spans, but it's not independent. If I was to set up that equation to test for independence, and set up a system of equations involving some like x1, x2, x3, right, trying to find some scalars so that a linear combination of these three vectors equals the 0 vector, I'd end up with this system, right, where the first, just matrix A, 1, -2 in the first column, 4, -8 in the second, -3, 6 in the third. right? And then some zeros on the other side, but I'm just going to write matrix A again. And we're going to put this into, I'm going to put this in reduced echelon form, reduced row echelon form. Again, not a crazy task here. I would very simply double the first row and add it to the second row. And look, the second row is just double the first row. So when I put this into reduced echelon form, I'd have 1, 4, -3 as the first row still, and then the second row is a bunch of zeros. And that's it. Right, there's a pivot position, right? This leading one in this first row here with zeros below and above it, and then there's no leading one in any of the rows beneath that, so I'm done. So this tells me that the only, in order to construct a set of actually, independent vectors, the only vector from the set I need is 1, -2, that first column. All right, the one corresponding to the pivot column here. All right, now be careful. Don't say 1, 0. All right, is a basis. Let me show you why. All right. Very often people make that mistake. They'll put it in row echelon form here, reduced row echelon form, and then just take the pivot columns themselves as the basis, but that's not the case. So let me go through this here. So what we're going to see here is that, and you can tell, right, 4, -8 is just 4 times that first vector, so I don't need it. Scratch it out. And -3, 6 is also just -3 times the first vector, times -1, 2, so I don't need that one either. And that's what this is saying. All right, that's what this reduced echelon form of the matrix helps me see. This first vector's good. I can a good vector, and then these other two are really unnecessary, right? These other two that correspond to non-pivot columns. So the column space of A is just the span of 1, -2. All right, just any scalar multiple of 1, -2. All right, so 4, -8 would be in here, -3, 6 would be in here, 5, -10 would be in here, multiplied by 5. Any scalar multiple, 0, 0's in there, any scalar multiple of that would be in the column space. All right, so it's just the span of that single vector. And that set, all right, and that set with just the vector 1, -2 in it is a basis for the column space. Right, it's the building block. Every vector in here is just a multiple of this one. Right, I can take this one and construct any vector in this, and it's obviously independent because it's a set of a single non-zero vector. All right. Now, like I was saying earlier, don't do this. Right, let me show you. Like I'll write a don't. Right, this is a mistake. So don't use the column, the pivot columns from RREF as your basis, and here's why. Put this in a bubble or something. This is big because, again, I see this mistake made too often. So let me show you why. What if you put it in reduced row echelon form, matrix A, put the matrix in reduced echelon form, and then you look at, hey, here's a pivot column, right? So you think the vector 1, 0 is a basis for the column space, and you make that statement. Well, let me show you why this is wrong. This is wrong because, what would belong in here, right? The column space of this matrix is, any multiple of -1, 2, or even any linear combination of these three. Take any of these three columns. The question is, could you form form. Can you form the vector, 1, -2? Can you, there's a column from A. Using only the vector 1, 0. This vector that, that's the pivot column of the reduced echelon form. The answer is no, you can't. Right? I can, if I take 1, 0 and say, how do I use this vector and only this vector, and multiples, scalar multiples of it, you can multiply this vector by any scalar, and the second component will always be 0. You're never going to get a second component of -2. So this is bad. All right, that's what I'm saying here in the bubble. Do not use columns, the pivot columns. Any columns really, but do not use the pivot columns from reduced echelon form as a basis. All right, it's only the vector, the columns from the original matrix that we're going to be using here as a valid basis for the column space. Okay, so I hope that's clear. All right, because don't want you doing that too much. If I don't want you doing that at all. What am I saying? Too much. I don't want you doing that at all. All right. Next. So here's another matrix. This one's a 3 by 3. So same question, what's the column space? Now again, the column space is easy to describe at first, but then we might want to shrink it down a bit. If the set of vectors is dependent, there are going to be some vectors you might not need. So I just scratch those out, right, like you saw me do in the last couple of examples. The column space of this matrix is the span of the columns, right? The column vectors, and those are, 7, -3, 4 there. The vector 6, 2, -1, and the vector 1, -8, 5. All right. Or you could write out, all linear the set of all linear combinations of these 3 vectors. All right, so now this is a little different than the previous 2 examples. This time, the number of vectors is equal to the number of components, so you can't automatically say that these are dependent, right? They might be independent, and we're going to again just check that by simply putting matrix A into reduced echelon form here, reduced row echelon form. And I'm not going to write it again. I'll just put the reduced row echelon form. Remember, if I was checking for independence, I would just have a bunch of zeros on the other side, but that would always stay zeros, so no need to write it really. This time I'm going to go to the calculator. All right, so turn this. I have an 84 plus here, just similar to an 83. If you've got it, go to the matrix menu here and edit matrix A, and this is enter the row 3 rows by 3 columns. Enter the size, then enter the entries. First row 7, 6, 1. Then second row 2, -8, and 4, -1, 5. Alright, and then we get out of here. Now I wish to put that matrix in, reduced row echelon form, RREF on the calculator. Go back to the matrix menu, over to math, scroll to where you see eventually RREF, and again, don't confuse it with REF. This is row echelon form or just plain old echelon form. I like reduced myself, so B there, and put matrix A under names in reduced row echelon form. And look, it's the identity matrix. So if you were setting this up, and there were zeros on the other side, that means that only the trivial solution, x1 equals 0, x2 equals 0, x3 equals 0, only the trivial solution would be a solution to the equation that you set up where you have a linear combination of these 3 columns equal to the 0 vector. So that means that these 3 columns are independent, right? Every single one of them. Every column is a pivot column, right? So the first vector from A the second vector from A. All three vectors from A are independent. So I can't shrink this set down. This is fine. This set of three vectors is a basis for the column space, and I'm just gonna so here's the column space of A. All right, it's just the set of all linear combinations of these three and the set with those three vectors would form a basis for the column space. Now, something else you might notice, these are all vectors from R3, right? This is actually a subspace of R3. And if you remember back, again, I'm hoping you remember that the dimension of R3 was 3, right? Every basis of R3 would have 3 independent vectors in it. This basis for this space has 3 independent vectors in it. So, in fact, the column space of A is all of R3. Right, kind of like the first example was all of R2 that I showed you today. So you could take any vector from R3 you wish, and it can be written as a linear combination of these three, right? And these three are independent. So these three vectors are some nice building blocks for R3. All right. Now, if you had made the mistake of using 1, 0, 0, 0, 1, 0, and 0, 0, 1, it wouldn't be wrong this time, because remember, that's the standard basis, which is, for R3, everything in R3 can be built with these three vectors here. But again, in general, that's going to be wrong. Right? You saw in the last example, you shouldn't just take the pivot columns of the reduced echelon form and make that your basis. So I mean, it would have been okay here, but again, in most cases, it might not be like you saw with the last example. So just go back to the make it easy on yourself, right? Just go back to the corresponding vector from the original matrix. All right, and then I have just one final example. So here I'm given this is a 3x4 matrix, asked to again do the same stuff. Find the column space and a basis for the column space of this matrix. Now right away I'm noticing that the first and second column are just scalar multiples. I multiply the first column by 3, I would get the second column. So I'm already seeing that one of these is unnecessary. Alright, but we'll see that when we again just take the matrix. Alright, first I'm going to write what the column space is. Alright, the column space is the span of these four vectors, and like I did with earlier examples, I'm going to just scratch some of them off that aren't necessary. Right, that can be written as linear combinations of the others. So negative 2, 1, 1, negative 6, 3, 3, 0, 1, negative 1, and 4, 4, negative 8. Alright, so obviously this set spans the space, right? Because by definition of span, right, every vector in this column space is a linear combination of these four. But they're dependent again, right? I have again that same scenario where there are more vectors in the set than there are components. But I'm going to do what I do for every example. Right. So we're going to take this matrix, put it in reduced row echelon form, reduced echelon form. And then, from there, very easily determine a nice basis for the column space. Alright, so this is, go back to the matrix here on the calculator. This is a 3x4. And enter the entries 6, 0, 4, 1, 3, 1, 4. 1, 3, negative 1, negative 8. Alright, and then the last thing I entered was reduce row echelon form, so I can just re-enter it by hitting second enter. And okay, there's a, you can very clearly see that not all of the columns are pivot columns, right? And I'll write this. You got 1, 0, 0 for the first column, 3, 0, 0 for the second, 0, 1, 0 for the third, and negative 2, 6, 0 for the fourth. And look for the pivot columns, right? Those leading ones in the rows. There's a leading one here. So the first column is a pivot column, meaning that first vector, negative 2, 1, 1, I'm going to keep that. All right, that'll be part of the base of a basis for the column space. And then the second row, the leading one, is in the third column. All right, so this third vector, this 0, 1, negative 1, that'll be a vector I keep. All right, that'll make up the basis. Third row is all zeros. There's no leading one. So that's it, just those two. Okay, so I'm going to keep negative 2, 1, 1. Get rid of negative 6, 3, 3. Keep 0, 1, negative 1, and get rid of 4, 4, negative 8. Right. So that means that, and you saw earlier, I already told you, this vector is definitely, 3 times this vector, so don't need that one. And then you could show that this last vector is a linear combination of these two that I kept. You could show that 4, 4, negative 8 is some linear combination of negative 2, 1, 1 and 0, 1, negative 1, but I'm not going to go into seeing what that would be. All right. Okay. So then, all right. So now the column space of A is just the span of these two vectors. Again, I should technically rewrite that, but I'm not going to. All right. Just know that the column space is now simply the span of these two vectors. Every vector in this space can be written as a linear combination of just these two. And the set with just those two vectors in it, with negative 2, 1, 1, and 0, 1, negative 1, is a basis for the column space, right, or the building blocks for the column space. Very quick and easy once you have your matrix in reduced echelon form. All right, and here's another example of where you wouldn't use, where you wouldn't use this set. All right, where you're like, oh, I put it in reduced echelon form, and like, hey, there's my pivot column 1, 0, 0, and there's another pivot column 0, 1, 0. That is not a basis. Again, look at that. Look at the third components of both of them. All right, the third components of both of these is 0. So how are you going to make this vector? How are you going to make that vector, which are clearly in the column space? They're clearly one of the columns of the matrix. So, this is yet another example as to why you don't use the pivot columns of reduced echelon form. You use the columns that correspond to those pivot columns in the original matrix as your basis. Okay, so pretty simple, I think. All right, once you got, again, I went over that first example. It was pretty long. I went over it in more depth, talking about what it meant to check for independence and all that. Some stuff you've hopefully seen and are a little familiar with. All right, so just given a matrix, column space is simply the set of all linear combinations of the columns. It'll be a subspace of some Euclidean space. Put it in reduced echelon form, and then each column of matrix A of the matrix that corresponds to the reduced echelon form's pivot columns, that set of vectors will form a nice basis for the column space of A, or the span of the columns of A. Right? So I hope you enjoy working on examples of like those, and thank you very much for watching.